Here we're going to talk about antiderivatives and the indefinite integral. Now what we've been doing for the last 6 or so weeks is computing derivatives and doing many applications of derivatives. But remember what the derivative is. Given a function, we can find a new function called its derivative. And there are many applications as we've seen. For example, given a position function, you can find a velocity function and an acceleration function by taking a derivative once or twice. But what if you want to do that same process but backwards? So say, for example, you want to find a position function given a velocity function. Well, you can't take the derivative of the velocity function. You'd have to go backwards. And that's what we mean by an antiderivative. You would have to take the antiderivative of, for example, velocity to find a potential position function. So to formally define the antiderivative, an antiderivative of the function f is a new function whose derivative is f. So it's relatively standard in antiderivative and indefinite integral discussion to have a lowercase f and a capital F. So here, notice, an antiderivative of the function lowercase f is a function whose derivative is lowercase f. Now, as a remark, just turning that definition into notation, math notation, capital F is an antiderivative of lowercase f if capital F prime equals f. So the derivative of capital F is lowercase f, so capital F is an antiderivative. So let's do this example. Find 3 antiderivatives of f of x equals 5x to the 4th. I'm not always going to say capital and lowercase. It'll be clear which one I mean. So find 3 antiderivatives of 5x to the 4th. So what we need here is a new function whose derivative is 5x to the 4th. Well, we've seen that a few times. I'm going to call it capital F. Well, this says to find 3 of them, so let's find 3 of them. I'm going to call them all capital F. That's okay. I could say like F1, F2, F3. I'm just going to say all are going to be capital F. We need a function whose derivative is 5x to the 4th. Well, we've seen many times that the derivative of x to the 5th is 5x to the 4th by the power rule. Right here, the derivative of capital F is lowercase f. Well, that's one of them. We need 2 more. Well, we know that the derivative of a constant is 0. So if we take this x to the 5th and add, say, 3 to it, for this second function, x to the 5th plus 3, the derivative is also 5x to the 4th plus 0, so that's 5x to the 4th. And that can be any constant. So a third example, or a third antiderivative could be x to the 5th minus any constant, minus pi, or minus root 2, or plus root 2, or plus 5,000 root 2. All 3 of these functions, when you take the derivative, you get 5x to the 4th. Now, you'll notice, like if we added any constant to that, we would have still gotten the same, we would have gotten another function whose antiderivative, or another function whose derivative is 5x to the 4th. But what if we said like 5x to the 4th plus x? Well, that derivative would no longer be 5x to the 4th, because we'd have 5x to the 4th plus 1. So we can't add onto this x to the 5th a function of x. All we can do is add constants. If we add a function of x, then the derivative will have another piece after 5x to the 4th, a piece which is not 0. And that gives us, that observation actually combined with corollary, I believe I called it corollary 2, of the mean value theorem, gives us this theorem, the general form of the antiderivative. Antiderivative is a long word, so sometimes I will abbreviate it. But the general form of the antiderivative. Let f of x be any let capital F be any antiderivative of lowercase f. Any other antiderivative of lowercase f is of the form f of x plus c. And c here, so where that says where c is a constant. So if we want an antiderivative, well, if we have an antiderivative of a function and we want more, well, all we have to do is throw other constants, well, add other constants onto that. And this definition here on the fourth board formalizes that theorem and assigns a nice notation and a nice word, a nice, word is a good enough word, to that situation. So here, definition, let f of x be a function. The indefinite integral of f of x, indefinite integral, I-N-D-F-I-N-I-T-E, integral of f of x denoted integral of f of x dx. In the next video, which is called the definite integral, we'll explain a little more about this notation. But right here, denoted integral sign f of x dx. The integral sign is just like a kind of a stretched out capital S. The integral sign there, it's like a stretched out capital. That's actually a pretty good integral sign I just drew. I will not take a picture of that because I drew a much nicer integral sign in my third or fourth year of undergrad while tutoring. But this is an integral sign. So here the indefinite integral of f of x denoted that sign f of x dx read the integral of f of x with respect to x or dx is the most general antiderivative of f of x. So this notation right here will always equal the most general antiderivative of f of x. That is, just combining that with this theorem, the integral of f of x dx equals capital F of x plus c, where capital F is an antiderivative of f of x and c is a constant. So let's do two examples. We'll do this one 5x to the fourth, and then we'll do another with a trig, because we know derivatives of trig functions. So let's just do two examples right here. Example. Find the indefinite integral, or evaluate, let's just say. Evaluate, we'll do a part A, the integral of 5x to the fourth with respect to x. With respect to x, just means x is our variable. Kind of like in the dy dx notation. That means we're differentiating with respect to x. And let's do the integral of cosine of x dx. Well, right here, we know that x to the fifth has derivative 5x to the fourth. So there's one antiderivative of f of x. Any other one is that plus a constant. So for this one, the integral of 5x to the fourth, we'll say it's x to the fifth plus c. And you don't always have to say, so down here I wrote where c is a constant both times. That'll probably be the last time I write where c is a constant. In these evaluations, you don't have to write where c is a constant. It's very standard in calculus to assume this capital C is the constant of integration. Now how about this next one? Cosine of x. Well, what do we need here? We need an antiderivative of cosine of x. We need a function whose derivative is cosine of x. Do we know any? Well, what do we have in trig? Derivative of tangent is secant squared. That's not going to help us. Derivative of cotangent, negative cosecant squared. That's not going to help. Derivative of cosine is negative sine. But that's not helpful here, because we don't want the derivative of cosine. We want a function whose derivative is cosine. Well, derivative of cosecant is negative cosecant cotangent. Derivative of sine is cosine. Well, what do you know? Derivative of sine is cosine. So that tells us that sine of x is an antiderivative of cosine of x. And once you find one antiderivative, any other antiderivative is that plus a constant. So the indefinite integral of cosine of x with respect to x is sine of x plus c. Now, when we were doing derivatives, we had a large list of derivative rules. And finding an antiderivative is just that same set of rules, but going backwards. Like here we had the power rule 5x to the fourth. The derivative of x to the fifth is 5x to the fourth. So what we're going to have next is a nice table of indefinite integrals. Now, I could give you a table of antiderivatives and then a table of indefinite integrals, but they would look basically the same. So I'm going to present them as a table of indefinite integrals, and in that you'll see that the antiderivatives are given as well. So let's look at the table of indefinite integrals. So here we have 7 indefinite integrals. There will be 6 more in a moment for the trig functions, but let's talk about these 7 first. The integral of k with respect to x is kx plus c. And here k is a constant. In all of these, c is going to be our constant of integration. So the integral of a constant is that constant times x, and that parallels the derivative result that the derivative of constant times x is just the constant. Next one, the power rule for integrals. So the power rule for derivatives said bring the exponent down and then multiply. Well, bring the exponent down, multiply, and then subtract 1 from the exponent. The integral rule for power functions like this is the same thing except opposite. So add 1 to the exponent and then divide. So the integral of x to the n, 1 over n plus 1 times x to the n plus 1, and then plus c. And you'll notice if n equals -1, this won't work because you'd get a 0 in the denominator. So for like x squared, the indefinite integral will be 1/3 x cubed plus c. In that example we did 5x to the fourth, well, ignoring the 5, we'll get a rule for that later. But for x to the fourth, you'd get 1/5 x to the fifth, and then the 5 and the 5th cancel by a rule that we'll see in a moment. The next one, well, this one doesn't work if n equals -1, but fortunately we can still do it if n equals -1. If n equals -1, you have x to the -1, which is the same as 1 over x. And the integral of 1 over x is log of the absolute value of x plus c. The absolute value is there because this x can be negative, but logarithm doesn't exist for negatives. So for x negative, the logarithm, you'd have to take logarithm of -x to make that logarithm of a positive, and then the derivative of log negative x, 1 over -x times -1, which equals 1 over x. So we throw the absolute value on there. You need the absolute value for it to be true. Next, derivative of e to the x is e to the x. So the indefinite integral of e to the x is also e to the x, but plus c. You always need the constant of integration. And next, we have the inverse trig. Derivative of inverse sine is 1 over root 1 minus x squared. So the antiderivative of 1 over root 1 minus x squared is the inverse sine. So the indefinite integral of 1 over root 1 minus x squared is the inverse sine of x plus c. And similarly, for the inverse tangent and the inverse secant, the antiderivative of 1 over 1 plus x squared is the inverse tangent. So the integral of 1 over 1 plus x squared is the inverse tangent plus c. And the inverse secant's derivative, 1 over x times root x squared minus 1. The integral of that is the inverse secant plus c. And for the trig functions, the derivative of sine is cosine. So the indefinite integral of cosine is sine of x plus c, as we saw in one of those examples. The derivative of cosine is negative sine. So the derivative of negative cosine is negative sine, which is positive sine. So the integral of sine with respect to x is negative cosine plus c. And similarly for the other 4 trig functions. The integral of secant squared is tangent plus c. The integral of cosecant cotangent is negative cosecant plus c. Derivative of secant tangent, and of course all of these have x's, is secant plus c. And the integral of negative cosecant squared is negative cotangent of x plus c. Sorry, I'm making sure I'm not stepping on my microphone. Now, when we were doing derivatives, there were a few convenient properties of limits that made derivative computations much easier to deal with. And we have a couple properties for the indefinite integral that will make our computations much easier. So here, let capital F and capital G be antiderivatives of lowercase f and lowercase g. Let k be a constant, then the integral of f of x plus or minus g of x with respect to x. When we were doing derivatives, we could do derivatives one piece at a time. So if you had the derivative of x to the fifth plus 6, then you could do the derivative of x to the fifth and then the derivative of 6 and add them together. You can do the same for the indefinite integrals. The integral of f plus or minus g is capital F plus or minus g and then plus c. Technically, you'd have two constants floating around here, f plus c and then g plus c, but we'll just smash those two constants together as one at the end. That's standard. One other convenience in derivative computations was that if you had a constant in front of your function and you want to take the derivative, you could just carry the constant through. And we can do that here as well. So the integral of k times f of x equals k times the integral of f of x with respect to x. So I took k out of the integral, and this equals k capital F of x, and then of course we need our constant of integration plus c. So let's do a few examples where we get used to some of these integral properties. So let's do three integrals. First, integral of 4x to the third minus e to the x plus 5x to the negative fourth. Next, we have integral x squared plus 2 plus root x all over x. And then last, integral of tangent times cosine, tangent x, cosine x. So for this first one, we have three things added together. And that first property of integrals said that we could do that integral by doing it one piece at a time. So let's do that. Let's first do the integral of 4x to the third. And then the second property said that we can pull constants out. So let's pull that negative out. Minus the integral of e to the x. Plus the integral of 5x to the negative fourth. Notice all of these have dx's. An integral needs a dx for it to be correct. Well, how do we do the first one, 4x to the third? Well, before we do any of that, let's just notice we have three integrals here. All of them are going to have a constant of integration. But let's just throw all those constants together as one constant at the end. So I'm not going to do x to the fourth plus c minus e to the x plus c plus whatever that one is plus c. I'm just going to do a plus c at the end. So let's do 4x to the third first. Well, the 4 comes through. We get the integral of 4, or we get 4 times the integral of x cubed. How do we do x cubed? Well, the second integral rule tells us how we can do the integral of x cubed. The second rule says that the antiderivative of x to the 3 is 1 over 3 plus 1. 3 plus 1 is 4, times x to the 3 plus 1. So the integral of x to the third is a quarter x to the fourth plus c, and then that other 4 carries through. So for the first piece, we just get an x to the fourth. So we get 4 times a quarter x to the fourth. What about the next one? Well, rule, I think it was 1, 2, 3, 4. I think it was rule 4 says that the integral of e to the x is e to the x plus c. But we have that negative there. We can't forget the negative. So we get negative e to the x. How about this last piece, 5x to the negative fourth? Well, let's do that on the side. 5x to the negative fourth with respect to x equals what? 5 times 1 over negative 4 plus 1 x to the negative 4 plus 1, and then a plus c. What's negative 4 plus 1? Negative 3. So we have 5 times 1 over negative 3, x to the negative 3, and then plus c. So we have negative 5/3 x to the negative 3, and then at the end we need a plus c. Now with these, we can actually check all of our answers by doing a derivative, because what we know here is that the derivative of that over there must equal this inside, this integrand. This inside piece, the inside function between the integral and the dx is called an integrand. So to check our work, we just take the derivative over here and see that it equals this. Well, what's the derivative of this? 4x cubed negative e to the x. What do you get? Negative 5 times a negative 3 divided by negative 3. I said too many negatives. Negative 5/3 times negative 3 gives you a positive 5. X to the negative 3 minus 1. So that's x to the negative 4 plus 0, and that is this. So that's correct. How about this next one? I will tell you right now, this is not the answer. This right here is not the answer. We can't do this piece by piece. We can't just jump straight into the fraction. We don't have an antiderivative rule for quotients. So when we did derivatives, we had a quotient rule. But for integrals, we don't have a quotient rule. We also don't have a product rule, unless one of the terms is a constant. So we can't just jump straight into this. We need to make this look like things in our integrals chart. Well, what can we do with this? Well, let's reduce the fraction. X squared divided by x is x. 2 divided by x is 2 divided by x. Root x over x is x to the negative half. So here you have a root x over root x. So root x will cancel on the top and the bottom, and you're left with a root x on the bottom, which is x to the negative half. Well, now we can do it piece by piece because they're just added together. Derivative, well, the antiderivative of x, well, we use the power rule. The exponent here is 1, so you get 1 over 1 plus 1 times x to the 1 plus 1. So that's a half x squared. What about this next one? 2 over x. Well, the 2 carries through from property 2 on the properties of integrals theorem. So then you have 2 times 1 over x. Well, 1 over x, you can't use a power rule on because it's x to the negative 1. But you can use rule 3, the logarithm rule. Integral of 1 over x is log x plus log absolute value x plus c. So the integral of 2 over x is 2 log of absolute value of x. And just like in the top, we're going to use only one constant. We're not going to put 3 constants there. And what about this last piece, x to the negative half? Well, x to the negative half, that's x to some number. X to some number, we can use rule 2, the power rule. 1 over, what was it, negative a half plus 1, x to the negative a half plus 1, using rule 2, power rule. What's negative a half plus 1? Well, if you have $1 and spend 50 cents, you're left with 50 cents. So we have 1 over a half times x to the half. Well, 1 over a half, that's a stupid looking fraction. Let's just write that as one fraction by multiplying by what's that word? Reciprocal. 1 divided by a half is 2. So we get 2x to the half. So plus 2x to the half, which you could write as 2 root x, and then plus c. So let's check our answer here. Notice it's not going to equal this immediately, but if we take the derivative over here and get this, then that will work. Derivative half x to the 2 is a half times 2x, so it's just x. That's good. Derivative of log x is 1 over x. So the derivative of 2 log x is 2 over x. Derivative of 2x to the half is 2 times a half times x to the negative half. 2 times a half, again, is 1. And the derivative of a constant is 0. How about this next one? We don't have, well, first remark, we don't have in Calc 1 the derivative, a function whose derivative is tangent x. We actually may have seen it a couple times, but we don't have a function whose derivative is tangent x. Maybe you can find one. You'll learn that in Calc 2. But even if we did have that, we couldn't just say this answer is whatever that would be times sine x. Because integrals of products, you can't just do the product of the integral. So what can we do here? Well, all I can think of to do here is rewrite everything in terms of sines and cosines and see if it simplifies. So let's do that. Equals integral, tangent is sine over cosine. So we have sine over cosine times cosine. Well, look at that. Cosines cancel. And we're left with integral of sine of x with respect to x. And rule 2 from the trig list, so that would be what? 1, 2, 3, 7, 8. Rule 9 overall in the integrals would give us this answer. The derivative of cosine is negative sine, so the derivative of negative cosine is sine. So the integral of sine is negative cosine of x plus c. Now, these do take some practice getting used to. Just like with derivatives, it took a good amount of time to get used to those rules. So definitely try the worksheet problems with these and the homework problems. But one other thing we're going to do with these integrals, this is a constant. This could be any constant. We could throw a condition on lowercase f, we could throw a condition on our capital F that allows us to solve for that constant. So we can say, like over here, if when you put x into this you get 6, well, you can use that condition to solve for c. Or if you put 0 in for x, you get 6, you can use that condition to solve for c. So if x equals 0, then that entire sum must evaluate to 6. Well, you get 0 minus 1 minus 0. Actually, you can't let x equal 0. If x equals 1, why can't you let x equal 0 up there? Exactly. You can't put zeros in the denominator. But if we said when x equals 5, c equals 10, or something like that, when x equals 5, y equals 10, well, then we can use that to solve for c. And we call them initial value problems. So let's look at a couple of types of initial value problems. So initial value, I probably should erase that, problems. So let's look at this one. Solve this initial value problem. So what is it? dy dx. So it gives you a derivative equals x squared plus 2, but y of 0 equals 3. So solve this initial value question. So here we're given a derivative. And we're given a condition on the original function y. Well, let's find y first. Given the derivative, now that we know indefinite integrals, we can find a family of potential y's. So let's say y equals the integral of x squared plus 2 with respect to x. Well, we can do that using the power rule on the first one. 2 plus 1 is 3, so you get a third x cubed. 2 is a constant, so the first rule said that the an antiderivative of the constant is the constant times x. That equals plus 2x. Forgot to hit shift there. But the indefinite integral tells us that this integral, tells us that there are infinitely many potential y's, depending on what that constant is. But this condition here tells us there's only one constant c which will satisfy that condition. So here, let's say using y of 0 equals 3, we find, well, y of 0 equals 3 means when x equals 0, y equals 3. So let's let y equal 3. So left side is 3. Let's let x equal 0. A third, 0 cubed, plus 2 times 0, plus c. So 3 equals what? 0 plus 0 plus c. So c equals 3. Well, c equals 3. Solve the initial value problem means that we actually want y as our answer. So the answer would be, well, I could say, so y equals, what is it? The third x cubed plus 2x plus 3. Let's throw that in a box. So we're given a condition, so we're given a derivative, and we're given a condition on the original function, the initial function, and we use that to find the value c. Now notice here, c happened to equal this number. That's not necessarily always the case. Like if we threw an e to the x, for example, in there, you get e to the 0 is 1. And these terms wouldn't all just go away. So you should be a little careful in your solving for c. Let's do another. Oh, actually, I have one that describes what I just said, except it's with trig functions. So let's solve another initial value question. dy dx equals negative sine of x, and y of 0, again, equals 3. I guess I didn't have to erase that. So y equals the integral of negative sine of x. Let's do this in a couple steps. This negative comes out front. And then we have the integral of sine of x. Well, rule 2, or that last example we did, tells us the integral of sine of x is negative cosine of x plus c. And then these two negatives cancel out to make it just cosine of x plus c. Check our work. The derivative of this is negative sine, so that works. So now let's find c. Y of 0 equals 3, so using y of 0 equals 3, we find 3 equals what? Cosine of 0 plus c. What's cosine of 0? Well, 0 is over here. That ordered pair is 1, 0. So cosine of 0 is 1. So 3 equals 1 plus c, so c equals 2. So to solve this, we have y, so I'll say y equals cosine of x plus 2. So the initial value questions could be phrased like that. Let's look at an application using acceleration, velocity, and position. So here, a car is traveling at 50 feet per second velocity. it begins to decelerate at 15 feet per second squared. Acceleration. Part A, how long until the car stops? Part B, how much does the car travel during this time period? So how many, feet does it travel from the time it begins to decelerate until it's completely stopped? Well, part A, how long until the car stops? Well, that's when the velocity is 0. So part A, we want when velocity, v of t, equals 0. Well, we don't have a velocity function during this deceleration period. We have a velocity function before that. That's not really helpful yet. But all we have is that the car decelerates at 15 feet per second squared. So the acceleration function is negative 15, decelerating. It's going slower at a faster rate. So a of t is negative 15. Well, we can use that to find velocity. So velocity is the integral of acceleration because the derivative of velocity is acceleration. And that equals what? The integral of negative 15. Not what I was about to write. With respect to t, rule 1 would tell us that that is negative 15t, but we need a constant of integration. How can we solve that constant? Well, the time, maybe I should have made a remark. I'll just write as a remark on the side up here. Remark, the time period considered is when it starts to decelerate. So I'll say 0 until when it stops. And time 0 is when it starts to decelerate. So time 0, we're just going to move our y-axis so that time 0 occurs when the when the car starts to decelerate. When that happens, at that instant, the car is traveling 50. So we'll say, but the velocity at the beginning of our deceleration period, the velocity at 0, equals 50 feet per second. Well, v of 0 equals 50. We can find c. So we'll say, so 50 equals negative 15 times 0 plus c. So c equals 50. Well, that's great, because now we have a velocity function. So velocity v of t equals negative 15t plus 50. This question didn't say to find the velocity function. This said to find how long it takes for the car to stop. So we need where the velocity is 0, and that'll give us the time after which it stops. And since we're defining our 0 to be at the beginning of the acceleration period, that will tell us how long it takes to stop. So maybe I'll just go up here. 0, we want to solve when velocity is 0. 0 equals negative 15t plus 50. Solve that for t, so add 15t, divide by 15. So t equals 50 over 15, which reduces. What does it reduce to? 10 thirds. So 10 thirds seconds. So this car stops after 10 thirds seconds. Okay, great. How much does the car travel during this time period? Well, we're defining our 0 to be when it starts to decelerate. So if a car is driving and it begins to decelerate here, and it stops here, so it decelerate there, begins to decelerate there, and it stops here, well, all we need is this distance to find how much the car travels during this time period. So we can say at position 0, or we can say at time 0, the car is at position 0. But that won't matter if we can't find a position function, which we can find, because position is the antiderivative of velocity, since the derivative of position is velocity. What's velocity? Integral negative 15t plus 50 dt. Well, here we just have to do a couple power rules. So the negative 15 carries through. We're left with the integral of t. T to the first, the integral would be, what, half t squared? So negative 15 halves t squared plus 50, using rule 1. Integral there would be 50t. And then again, we're going to have another constant. I'm going to call it another c. To be perfectly perfect, I should probably call the first one like a c1 and a c2. Don't worry about that. If you take Calc 2 or Calc 3, there might be some examples where it is useful to differentiate between constants. Here, I'm not too concerned with it. Well, okay, we have our position function. Let's find c. Well, we already said at position 0, or at time 0, we're going to assume it's position 0. So I'll say, but s of 0 equals 0. So s of t, So 0 equals negative 15 halves 0 squared plus 50 times 0 plus c equals 0 plus c equals c. So c equals 0. So our position function, s of t, is what? Negative 15 halves t squared plus 50 t plus 0. I'm not going to write the plus 0. But this question didn't ask us to find the position function. It asked us how much does it travel in the time it takes to stop. Well, we already defined position 0 to be 0, so what we really need is s of 10/3 minus s of 0, but since we're defining that as our 0, all we need is s of 10/3, so I'll do that over here. So s of 10/3 equals what? Negative 15 halves times 10/3 squared times 100 over 9 plus 50 times 10/3. Let's just add those together. This one reduces a little at the beginning. What does that equal? Negative 3 times 50. No. Negative 5 times 50 over 3. So to do that, what? You cancel out the 2 with the 100, you get 50. You cancel out a 15 and a 9, you cancel a 3 from those. You're left with a 3 down there and a 5 up there. So you get negative 5 times 50 all over 3 plus 500 over 3, which equals negative 250 over 3 plus 500 over 3, which is just 250 over 3, and our units were feet. So it travels 250 over 3 feet. So here, the observations were that derivative of position is velocity, derivative of velocity is acceleration. So you could do that backwards. Antiderivative of acceleration is velocity, antiderivative of velocity is position.